organize dissemination activities as part of Great to Excel, including webinars. So today it's actually the sixth webinar we have been organizing. And every time we invite experts from our consortium to share knowledge and expertise about the project outputs. So today I'm very pleased to welcome Sergej Skornšek from the company Gorenje Toolmaking based in Slovenia. Sergej is a project manager working in production and quality control, and Gorenje is one of the industrial use cases of Great to Excel. And so we are very much looking forward to hear Sergej explain a little bit the expectations from an industrial point of view regarding the application of WAAM and additive manufacturing to the tool making production. And in a second time, we will have Professor Wim VAN PAEPEGEM from the University of Ghent, providing us with an overview from the research point of view on topology optimization, state-of-the-art techniques and potential applications. So I'm very happy to leave the floor now to Sergej. Feel free to write your questions during the presentations in the chat. We will have a few minutes after the end of each presentation to reply to your questions.
From my side, I would like to present you our participation of Gorenje Toolmaking company in this Great to Excel project. And firstly, I will shortly present you our company, and then I will continue with presentation of our 3 demonstrators included into the project. So Gorenje is one of the major toolmaking companies in Slovenia, and we have more than 70 years of experiences in toolmaking industry. Of this, almost 30 years in automotive industry. Our core business involves development, manufacturing, marketing, and maintenance of a variety of tools, mainly meant for sheet metal forming, injection molding, styrofoam packaging, and thermoforming. Side processes in our company are also production of parts for automotive industry and overall industry automatization and robotization. Our company consists of different processes which support the project from the beginning to the final acceptance at the buyer. From the project Great to Excel, we expect several benefits from results of WAAM technology for our tooling parts. Because of these reasons, we have chosen 3 different demonstrators for the tests with the goal to reduce costs, environmental effects, increase lifetime, and reduce production lead time and scrap, which is accumulated in the production. I will shortly present you each of demonstrator and current results of the tests which have been done so far. So the first demonstrator is called B4.1, and this is a tooling insert out of the tool for production of car parts. The insert is meant to cut the shape of the final part out of the sheet metal. For our tested inserts, we have chosen core material of GGG70, which is cast iron. Added material and process of welding have been done by the RM lab. Later, I will also present you some results which we have done in the past. The general expectations of WAAM process for these inserts are fast rework of inserts, less scrap produced during the production. We also expect increased lifetime when the quality of the process will meet the required quality, and by the end there will be a big benefit for us, the lower production costs due to decreased machining and a lower usage of the materials. So for demonstrator B 4.1, we have done inspection of weld qualities, and we are searching for possible splits, porosity, cavity, and some lack of fusion in the weld in the welds. For this particular demonstrator, we have found some major mistakes which have occurred during the process of welding. And one of the biggest here is lack of fusion between the core material and added material. So during the process of the production, there is a possibility that the added material can be teared off the core material. And the second quality issue here was also the cavities, which can be seen on the lower picture, and these cavities can leave some bigger burrs on the final parts, which will be produced in the tool. The second test which was made was measurements of hardness of added material, and also here we did not meet the required 56 HRC as we usually have in the tooling. So at the end we decide to produce new sample coupons which have been sent back to RAM lab, and they need to repeat the process of welding and choose different better material that these minimum requirements will be fulfilled, and then we can continue with tests in the production. The second demonstrator is similar as the first one. Here is also tooling insert from the tool for automotive industry, and also this insert is meant to cutting the shape of the final parts out of sheet metal. The core material for this insert was chosen regular steel. This is base material used in tooling industry, and the weld material was also chosen by RAM lab, and it is the same for both inserts. The expectations for these inserts are in general the same as in previous one. So to reduce the scraps, increase lifetime, and the major point here is that the maintenance of this insert is regular, so we want to achieve faster reworks of these inserts. The tests which we have done are the same as for B4.1, because also the requirements of the inserts are the same. So we have checked the weld quality, and for this demonstrator we have found that the weld was not consistent, and the mechanical process of cutting the insert with wire erosion was not possible because of the porous material. Because of this quality of the weld, we expect that the final insert with this quality will last no longer than 10% of usual lifetime expectancy for these cutting inserts. The hardness was also less than 50% of required, and this is the reason why we need to repeat the process of welding and choose better material to put the inserts into the actual tools and try them in the production. And the last, third demonstrator is also a tooling insert. In this case, insert out of the tool for white goods industry, and the insert is meant to produce the bottom of the drum in the washing machine. This is a forming insert, so that means that the formed material flows through the lower and upper inserts in the time when they are pressed together. The most important here is sliding properties of the material. So usually for these tools, we are using kind of bronze alloy with the name of AMCO. And for this testing demonstrator, we have chosen usual material, core material with the offset for place to add welding material, and the RAM lab have chosen a different bronze alloy. And after the results of the tests, we have also noticed some bad quality, and this can sorry, I missed something. So the benefits of this is that we did not choose to proceed with welding of this additional material to the core base material prepared for the test, because this is a bigger insert, and before we implement the welding on the test coupon, we need to be sure that the weld material will meet the required specifications. So after the weld inspections, we noticed some lack of fusion between the base material and added welded material, and we expect that during the process of forming, added material will be teared off of the core material. The hardness for this material is not the most important topic. So even that we did not achieve required 36 RCS, we decided to go on with the tests, and we have sent 2 sample coupons for tests of sliding properties. For now, we are still waiting for the results, and if we will find that the sliding properties can meet the same requirements as our current material, then we will proceed with welding on the actual part and milling, and then tests in the production. And this we expect in next 2 weeks, and then we can hopefully with good results, start with the tests in our production and gain some more informations. So from my side, this was some short review of the project and current status and informations that we have gained. And yeah, thank you for the word. And if you have any questions, do not hesitate to ask.
Thank you very much, Sergej, and we look forward to see to find out more about the demonstrators by the end of the Great to Excel project. Maybe we will do another webinar for you to show us the results.
So, good afternoon, ladies and gentlemen, or maybe good morning or good evening. I don't know in which time zone you are. So, my name is Wim VAN PAEPEGEM, and I present this on behalf of one of our senior postdocs who contributed a lot to this work, Tien Dung Ying, and myself, Wim VAN PAEPEGEM. And we are working at the Faculty of Engineering in Ghent University, which is a university in Belgium. And we are partner in the Great to Excel project. So what I would like to explain you today a bit is about topology optimization and how it can connect to additive manufacturing, and also the relation to the some of the challenging use cases we have in Great to Excel that also required us to develop new features of the topology optimization. What you can expect in the coming half an hour, more or less, I will not bother you too much about who we are, so I just have one slide to give you a bit an idea what we are working in or what we are as a university group are doing in the field of additive manufacturing. Then, since I don't know your background, I have a small introduction on topology optimization to make sure that you all understand what we define as topology optimization in this context. Then I will try to let you a bit feel what kind of requirements the Great to Excel project poses on the topology optimization, and then some new developments that we did, which are related to both thermal and mechanical loading at the same time, having more than one material to choose from in the topology optimization, and having maybe local constraints on, for example, limiting the stresses in a certain area or limiting the maximum displacement in a certain area, and then a little outlook what we are still now working on in the project. So this outline will come back, and in this way you can follow a bit the structure of this presentation. So first of all, who are we? The text at the left is not so important. Just for the recording, you have done a bit more details. I will just guide you through it very quickly with a few animations that I hope are also running at your side. So for additive manufacturing, we do some simulation work on deposition of material. Here you see deposition of polymer, and can also be like mortar or concrete. So you have a sort of slurry that you deposit, and depending on the rheology and the setting time, you can see if you can build up different layers, or they will collapse, or they will deform too much. We also work on metals a lot. So this is 3D printed titanium. So we do testing on fatigue behavior, multi-axial fatigue behavior. And you see here a €1 coin. So these are really tiny samples. This is also to limit the cost, because as you know, 3D printed metals are not that cheap. So to limit a bit the cost of coupons. Another field is NDT. So this is non-destructive testing. If you have here, this is also 3D printed titanium. This is for engine applications. So if you have printed a vane, how do you know it's a good one? And you would like to know that in a few seconds. So we use high frequency vibration techniques where we inject vibrations at different points, and then can decide if this is a good printed part or a bad one in just literally 3 seconds. We cannot tell you what damage it is and where it is, but we can just say it's a good or a bad. And then some applications here for biomedical applications of 3D printed implants, lattice structures, 3D printed braces. And then also here you see a first movie of topology optimization. So that's what I will focus on for the rest of the presentation. So that was very briefly what we are mainly doing in this field. And now I will introduce you a bit to topology optimization. First of all, what is it? And I mean in the context of mechanics and loading of structures. The meaning is that you have a certain a volume of material, you have a certain load, and the question is then, what is the ideal placement of material if you have a given load, which is here? You have given boundary conditions that it's clamped here, and you might have certain constraints which are typically trying to get a minimum mass, so as light as possible, and have a maximize the system performance, which is most of the time like having a maximum stiffness for a minimum mass. I show you here some simple examples to introduce the topic and to get you a bit familiar with the concept. So if you have initially all this here filled with material and you try to find the lightest solution with the maximum stiffness, then you will end up with something like this. So you see that there are iterations running, so you cannot solve that in one iteration. And you see that in the beginning you have material everywhere, then it starts to somehow concentrate in certain areas. And then gradually more and more material is removed in other areas. And in the end, you have this result. And basically you like to end up with a black and white solution. In terms of machining, you want to have clear boundaries where there is no material and where there is solid material. So this is topology optimization. Just a few more things that can be said about it. What can be your objectives? What do you want to optimize? So most of the time performance. This can be in mechanics, typically high stiffness, low mass, not too high stresses, not exaggerated displacements, preferably with a minimum amount of material. Maybe stresses should remain like below the yield stress or half of the yield stress. And you can also control in an implicit way the manufacturability. For example, here I have another simple case, a plate clamped at the left side, just a point load here. And then here you see again the iterations, how it converges to a certain solution. And this is what you intuitively can a bit think of. And the force is here it's clamped and you get a sort of truss structure. Now, depending on how much you, we will see it later, how much you filter, you can have this with quite massive material sections, let's say, or you can make it finer and finer, which can sometimes have similar performance, but you can imagine to produce this, and certainly with classical machining methods, would be much harder than this one. And the last few slides just to give you a bit understanding how this method works. Most of the topology optimization methods are based on the SIMP method, and it's an abbreviation, and it stands for solid isotropic material with penalization. And what does it mean? So your initial block of material is discretized in small volumes. Each volume has a density, so with the symbol rho, and the density can, in a normalized way, vary between 0 and 1. 0 is there is no material, just air or void, and 1 means it's solid material. And every single one of these densities can change between 0 and 1. This is already important because if you have a very big volume and many of these small elements, it means that your degrees of freedom can be 100,000s or millions of these densities that can be different. And then you will iteratively, that's what you saw in the previous slides in the animations, you update every time the density. And then, for example, you see in this block of material that does not contribute much to the loading. So here the density will start to go down. While this element, that's a very important one, and there we need certainly mass, and the material should stay there. Because we don't like that much that the density is either 0, either 1, but in between, we typically don't like that because like a density of half normalized, yeah, what does it mean? There is half material there and half not. So we typically have a sort of penalization, and that's where this term comes from. So you try to push, the red line is basically the relation here between the stiffness and the density, and you make it nonlinear to push it to the two boundaries, to push it to 0 or to push it to 1, and preferably not in the intermediate region. And the last thing, and then I'm done with the introduction, for those who are a bit more familiar with this, another thing that you need to know, because I said in the previous slide, you iteratively update the densities, but yeah, in which direction should the density increase or decrease in a certain element? So you need to calculate how much the C is the compliance, that's the inverse of the stiffness, so how soft the structure or how compliant the structure is. What is the dependency of the compliance on the density in that element? And that's a mathematical function you have to calculate. And of course, the less loading that that particular element sees, the less it contributes to the compliance and the more it can be removed. And then what I said about the filtering, how if you have then a different pattern of densities, big density here and here almost 0 and there a bit more again, you somehow filter that a bit to get a bit printable or manufacturable solution. And that refers also to here, like the filter radius, you can change it and in this way get a bit different resolution, let's say, of your solution. And just to finish off the introduction, just a few more examples to give you just a bit of feeling of what kind of structures you can get. So here you start with a big block of material. It's a distributed loading. And what do you get in the end after all these iterations here? You see it starts with a block of material and gradually it concentrates in certain areas. And you see that the top is always black. So you can also, that's called frozen areas. So this area, you say there must be material always because my load has to be introduced. So also in certain areas of your structure, you can say this always there has to be mass in this area because I need a bolted connection there or I need a weld there or whatever. You can also, of course, go to 3D. Here you have a bracket solution. And I show this once because once you go to 3D means many more of these small elements with the density. So the number of degrees of freedom, the number of unknowns, all these densities in all these elements quickly get very large. You see it's 50 by 50 by 13 is the number in the initial box. And yeah, if you make the discretization finer and you take it 100 by 100 by 26, for example, it goes very quickly that it goes much larger in number of unknowns. And you see again the effect of the filtering, finer filtering and a coarser filtering, and then you see that you get more massive-like structures in it. And the last one, and this is just a bit similar, but then in 3D, but still a quite coarse solution here. Okay, so that's a bit to let you understand what topology optimization is. Now, if you look to the technology of additive manufacturing, basically there is a very natural marriage, you can say, between topology optimization and additive manufacturing. And why is that? Because topology optimization typically gives you quite organic shapes, which are smooth, which are not really meant for classical machining like CNC and turning and milling. But with 3D printing, you can make this. So the shapes that you generate with topology optimization often have to be corrected quite a lot to make them machinable with classical machining methods, also like this one, for example. But with additive manufacturing, you can do that more naturally. So it's a quite logical combination if you go to design and you do 3D printing to also think about topology optimization to have a more optimized solution of your structure. And just the last word about this curve that you just saw. So you had the stiffness versus the normalized density, and we said we want to push it to 0 and push it to 1 because a half density is a bit strange. Now in 3D printing, you can add something additionally, is to print lattice structures. So to print like cellular, they're also sometimes called cellular structures, or if you wish, a sort of foam-like structure. And then, of course, the cube is not completely filled with material and also not completely void. So it is halfway filled with material. So then you can have indeed a half density, which really means something physical. It makes sense to then fill in material with half a density. So then you can think of structures like this, where you have solid material, and then at the boundaries, for example, you have lattice structures. This is not always for pure mechanical reasons. For example, in biomedical applications, they use it a lot to have bone ingrowth. So to have the bone growing into the implant, they use these cellular structures at the interface to have a good entanglement of the bone cells and have the growth into the implant. And we also have to make it sure that we can deal with large problems. So here, this is, for example, extremely fine discretization. This is about 1 million elements. That means we have about 1 million densities that we have to optimize for. It's also in 3D. And that we make it computationally efficient so that you can solve for really large-scale industrial problems and not just for a simple case. So in our code, that is already foreseen. And then a word about the requirements for the Grey2Excel project. When we started this, you know, maybe from previous seminars or from a flyer or a brochure of Grey2Excel. So the technology is WAAM, Wire Arc Additive Manufacturing. Here you see some pictures from Ramlab, which is another partner in the project. So they use a welding torch on a robot and they deposit bead by bead. Here you can see it clearly. And in this way, you deposit material. So what, if we think of topology optimization, what are then the requirements that we need? And therefore, I show you the use case we are mainly working on for this is a production mold. So this is another partner in the project is GKN. So they produce composite parts for aerospace, for helicopters. And they use, of course, metallic molds where inside the composite is produced. So here you see one of their molds. You see it's a conventional design with stiffened plates. You see here the heating and cooling channels. And inside, but you cannot see it here, inside is a cavity, and there is the part being produced. To make that part, they need to apply pressure and they need to apply temperature. So here you see the cycle over time. So yeah, basically just important is here the pressure is increasing and the temperature is increasing, and then you cure, you bake the composite that is inside this cavity. So what is important for us, the mold itself is subjected to temperature and pressure at the same time. So there are two kinds of loads. And then another thing which is important is that in Grey2Excel, it's also considered to have more than one welding torch in the melt pool at the same time. So you can create a different alloy at a different position. So that means that we can also do topology optimization with more than one material where we can choose from. For example, two materials with the same stiffness, but the thermal expansion coefficient of one of them is double of the other one. You can think of, for example, to control the distortion of this mold or to restrict certain deformations, that you can choose from more than one material. And then we need to start from something to implement all these things. So we had already an existing topology optimization code in our group, and it works like this. So this is a standalone master code, let's say. This is our in-house code, which does all the features of the topology optimization. And then basically in every iteration, because if I quickly go back, you had here, for example, here you have all the iterations running. So in every iteration, you have the load here on top, and you calculate the solution. You calculate the stresses, the strains, the displacement. So you have many iterations. And for every iteration, we call basically any commercial finite element solver that solves the mechanical, and in this case, thermomechanical problem. And then we do the topology optimization to decide what will be the new densities. And then we do the run again until it converges to a certain solution. So what are the new developments that we need? We have thermal and mechanical loading, like I explained you. We have multi-material possibilities, and we can have local constraints like the distortion should be limited or the stress should stay below a safe level. And these are not common, or let's say very rare to find in commercial topology optimization software, and some of them completely not. So those features were all built in our code, and I would go through the three different aspects to give you a bit of feeling how sometimes counterintuitive the results become when you have not a classical mechanical loading. So here are briefly listed the extensions we had to make. So to have thermal and mechanical loading, to allow for more than one material, to have a user-defined objective function. For example, in that area, I want low stress, or in that area, I want the displacement to be as small as possible. That is what they mean with the user-defined objective function. And to have also not a black box solver, but really have control about the solver for the optimization. That's basically the solver that drives the different iterations of the optimization. And a few other, let's say, second priority extensions was a bit about visualization, how you can nicely show the result. Also, how can you transfer this to a 3D printer software so that you can directly inject this geometry into converting it to G-code for printing it. And also computation efficiency is very important. We also made already some extensions for deep learning, but that's not so important for today. So now briefly, in my last section of my presentation, some new developments. First, thermomechanical loading. I want to give you a bit of feeling how our engineering intuition starts to fail a bit if you do that. Here you see, I give you therefore a few simple examples to feel it. This is a clamped plate. You just have a load in the middle. And suppose the temperature is not there, so it's just a purely mechanical problem. And then you do topology optimization. The solution that you will find is this one. So all the rest is 0. And here you have the load in the middle. And this is a typical like a sort of cable network or something. And every time, just to give you some confidence that we properly benchmarked and verified all our developments. So every time where we had a source from literature, we compared also with literature. And the only thing you do now is add a temperature difference of 5 degrees. So what does it mean? This plate wants to expand, and wants to also in this direction get larger because you heat it up. But the rigid walls are there, so it cannot expand. So you create additional stresses in the plate. And on top of that, you have the force. And now you get this kind of optimized solution. It's totally different than this one. You still have here the connection to introduce the force, but it becomes a very different solution. And also in literature, they find something else. And moreover, it becomes important what is the ratio between the temperature and the force. If the force is very high and the temperature very small, it does not matter. If you change the ratio, you get another solution. For example, in the next slide, you have again, it's another from another benchmark. You have again the force, the two clamped edges, again a delta T, a difference in temperature, but now the ratio is different between them and you get another solution. Yeah, here the literature solution is not so great because you have what they call a checkerboard pattern. That means that the filtering is not so well implemented. And then if you have a gradient of temperature from left to right, then you see that you even get a non-symmetric solution, that it's here a bit coming lower than there. But not the kind of solutions you would directly expect. Then multi-material topology optimization, that's also not such an easy one. Now the question is, suppose you have a block of material, you have three loads here, they are scaled, so they are more or less unit loads. And suppose now you can choose from three materials. So the blue, red and black will also be the colors in the next slides. They have a different density, they have a different stiffness, and they also, in this case, have a different cost function. So one is more expensive than the other. And here you see it graphically demonstrated. So the density of the three materials ranked with each other and their stiffness and cost. And now which material to put where? So the question is now you have three materials to choose from. Which material do you put where? If you still want to, for example, maximize the stiffness for the lowest mass. And now this would be with a single material. This still looks like a bit a classical solution. One force, second force, first force, and you have this solution. With more than one material, it becomes something like this. And obviously the goal is to outperform this solution. So this solution behaves better than this one. But you have three different materials, so the blue, the red, and the black. You also see that the solutions become typically non-unique. So for example, here we have a solution which is not exactly the same as literature. Our solution is a bit better because the compliance, so the inverse of the stiffness. So if the stiffness is higher, the compliance is lower. So our compliance is a bit lower than the one from literature. So it's a bit better solution, but it also looks a bit different. And also that's more a detail, but depending on the solver, you can also get different solutions every time. Just a bit quicker, these are a bit all similar, but again, for example, another one where it's clamped at the edge and you have a point load and a temperature difference. And now you can choose between two materials, Invar and 304L material, steel. And this is, for example, then the distribution with two materials and in literature. So it gets a bit non-intuitive how to distribute those two materials. And here is another one, a bit similar like the L profile I showed you before with a point load. Here also temperature difference. And here you see our solution and the solution from literature. You see our compliance is again a little bit smaller, so stiffer. And our material is a bit more integrated with each other, while here it's all green at the boundary and blue in the center, but they are quite alike. And the last one I want to show you just to see a bit the difference. Here you have two materials, titanium and high-strength steel. You see different densities, different stiffnesses, and also, of course, different thermal expansion coefficient. And again, similar, you have a force in the middle and you have a temperature difference. What is the optimal solution? What I want to show you here once is what if you have the single material solutions. So this is with material A, the solution. This is with material B. This is with material A plus B. And this is literature also with material A plus B. So again, if you look to the stiffness or the inverse, the compliance, you see that this solution outperforms the two other solutions which have higher compliance, so a lower stiffness. For the same, MF means the mass factor, so for the same amount of material. And here's the last what I want to show about this, is that now you see it integrated in one slide. On the columns, on the rows, you have material A alone, material B alone, and a combination of materials. And below is just a comparison with literature. And on the columns, you have the delta T. So 0 means a pure mechanical load. And then you start to add an increasing amount of temperature difference. And then you see for a single material, the solution changes a lot when the temperature changes. Depending on the type of material, it also changes because material A and B have different stiffness and thermal expansion coefficient. And if you combine them, most of the time, which is in bold, is always the lowest. So most of the time they outperform the single material solutions, but not always. Like here, the single material solution is the best, and like here also. So many different combinations that are not so easy to judge anymore. And the last thing is local constraints. So that means, for example, to minimize the stress. So here you have, you say that the stress should stay under a certain limit. For example, the yield stress or a fraction of the yield stress. And there you then get also a solution which is again different because you have a different constraint. And you see here that there is quite some intermediate material, so this half density material. So then you need to add some additional filtering again to make sure that intermediate material is disappearing as much as possible. This was stress-based. You also can do that for displacement-based. For example, if you say I have here the force and now no temperature yet, I want to minimize the displacements in this plate. If you first do the regular optimization just for maximum stiffness, you will get, you pull here and you get a deflection. And now with minimizing the displacement, the topology optimization suggests you to make some holes here. And by making these holes, you introduce a bit bending here, which reduces the displacement here. If you look to the displacement magnitude, you see here it's 0.012, and here it's 0.0094. So the displacement overall, you see it also at the maximum, is smaller. And if you add temperature with it, so now we add a temperature difference, you see that it gets even much more different. This is the without displacement constraint, so it moves here a lot. And now with displacement constraint, you get something like this. So again, you see 2.7 millimeter and here 0.7 millimeter, so displacements are very different. And I hope you agree, shapes that you would not immediately invent yourself when you look at this problem. So what is the outlook? Right now we are we have enough confidence in the code and we implement this to the mold. Here you see in top view the top of the mold, and you see here the more organic or natural distribution of material. You still see these vertical lines. These are the cooling channels and heating channels. So for the moment, these are not part of the optimization. So these are these here. So they are still straight. And the material is like distributed on top in a more organic way that you can also print. And we compared where possible also with commercial solvers to get confidence in our methods, like here is shown at the right. And right now, we are busy with the big mold of GKN. So this is a 2-meter mold for production of composite. You can recognize here already a bit the shape of the cavity where the material is formed. You have the cooling channels, which are frozen areas, so the cooling channels have to remain. And now we are doing the topology optimization for combined thermal mechanical loading and also multi-material solutions with different thermal expansion coefficient to this mold. So that's more or less it. Just the last second to conclude. You can, of course, also apply this in other fields, like here is topology optimization for a joint here, which is making your jaw move relative to the skull. And if there is an implant to replace this joint, this is the original design with a lot of screws here, and the topology optimization drives you rather to this design where there is more anchoring needed here and much less screws there. And then you can also do sizing optimization on the local thickness, but it gives you a quite different solution. And the same, for example, for patients who have suffered injuries or from cancer or a traffic accident, and you need to replace part of the jaw. Then we also have topology optimization to have a sort of replacing titanium structure that where then artificial teeth can be embedded so that people can bite again and eat again more naturally. So that was the last slide, and to wrap up, so we have a good code now that can deal with many things. We can also solve in 3D with large number of degrees of freedom, and we are also now expanding to other problems, combining with electromagnetic fields, looking at heat exchanger problems where we think there are also potential because they also have thermal and mechanical fields, and that's basically to conclude this presentation. So I thank you for your attention, and this was all I had to say. I will stop sharing so that I see you if anybody wants to ask any question. Thank you very much.
Yes, please go ahead.
I'm Johan Bonaventure from MAN in France. Just a small question, maybe. Such software shall not be available on the market, I guess, no?
No, yeah, let's say most commercial topology optimization software is first of all targeted to pure mechanical problems, which is what most engineers are familiar with. I don't claim that I know all the latest developments of every single software developer, but I think like once you start to combine with temperature loading, because we also look at like thermal convection and conduction, which is also important for this application of the mold, because internally you have the high temperature, but of course around there is room temperature, so I also have a gradient of the heat. And then the multi-material, that's also... And a third thing which we really observe, if we compare with commercial software, you have a few parameters to tune the solver, but you don't really know very well how it's implemented. So our is not a black box. We know how we can control the solver. And from the start already, when we started with the pure mechanical implementation, we have always said we want to solve industrial problems. Also, to give you an idea, for a few 100,000 degrees of freedom, we can run it in 7-8 hours, 50 to 100 iterations, which I think is quite fast for this kind of problems. So we have always been looking, because there is a quite big discrepancy. I don't know if you noticed it in the presentation, but almost all the benchmarks that we do, that you find in literature, are 2D, very small, with simple loads. And once you go to 3D and complex loads, there is no reference anymore. There is no benchmark. And you need to trust your code. So that's why we do so many benchmarks, to really be sure if you extrapolate from 2D to 3D and to more complex loads, then you have to trust your code, because often the solution is not so intuitive anymore. But if you're interested to learn some more, I don't know the audience now, so I stayed a bit in general about topology optimization. If you're interested, we can have a separate discussion more in the technical details, how it works. But it's yeah, that's more or less an answer to your question, I hope.
Thank you very much. I just discovered the topic.
Okay. Yeah, that's what the webinars are for, to learn something new.
Thank you.
You're welcome.
It's just time to thank everyone for the participation, and specifically thanks to Sergej and Wim for the very nice presentations. We will put the record of this webinar available on the Grade2Excel website, and we will organize some more webinars in the next month. So just stay tuned and feel free to contact us at PolyMC2 if you wish to know more about the project and our speakers. So thank you everyone, and we wish you a good afternoon and a nice weekend ahead.